Hello, today we're going to talk about functions. We'll be studying many functions throughout the course, so today we'll just have a brief introduction as to what a function is. Now, in the hard sciences, in economics, in psychology, we're often interested in studying the relationship between two varying quantities. Like in economics, we might be interested in studying how the demand for a particular product depends on how much we charge for that product. In biology, we might be interested in studying how the population of predators in a certain area depends on the population of prey. In physics, we might study how the velocity of a particle depends on the time elapsed since we started observing it. Now, all of those are just called relations. They are relationships between two unknown quantities. Now, if we say that one of the quantities depends on the other, for instance, in the economics example, we have that the demand for the product we could call that D, depends on the price per unit. Of course, if we increase the price per unit, then the demand will go down. If we decrease the price per unit, make it cheaper, then demand should go up. That's usually what we expect. Now, if D depends on P, if those are the variables I've chosen, then we'd call D the dependent variable. And P is the independent variable. Now that's just in general for relations. However, if I want to talk about functions, they are very special types of relations. They have the very special property that for each possible value of our independent variable, we get a unique value of the dependent variable. When that happens, we have a function. So for instance, if we think of our particle in physics that's moving around, and we're studying its velocity and how it's related to the time elapsed that we've been observing it, let's set up some variables. So let's set up our independent variable first, time. So let t be the time elapsed in seconds. Let's let v be the velocity of the particle. In meters per second. Okay. And if that's the case, we'd usually say that the velocity depends on the time elapsed. So our time is the independent variable, and our velocity is the dependent variable. Now, what makes this a function? Well, if we really think about it carefully, this is only a function if we're only going to look at this once for a particular particle. So, if I think of my particle moving around, it's got a certain time, and if we check our watch at that exact moment in time, there's going to be a unique velocity. Okay? We won't look at our speedometer and see two different speeds for our particle at the same time. No, at 7 seconds into the experiment, if we check the speedometer, it'll be going 13 meters per second. It won't be going 13 meters per second and also 17 meters per second. That will never happen. Okay? So a function, and often we label those with f, has been created here. We have an independent variable t, and for each value of the independent variable, we get one value of the dependent variable. Each time has exactly one speed. So that's a function. Now that's the definition, but of course we like to use functions in an algebraic context. So we have some notation to describe functions. So if y is our dependent variable and x is our independent variable and f is the name for the function, then we would write down this expression here. We've got our function whose name is f. It's kind of like a black box. It takes in inputs x and produces outputs y. Okay? So you give it a value x. It does something magical. We really don't know what, or maybe we do, but it can change. And it produces some output y. Now this notation that you see above, you would read it as y equals f of x. So that's how you would read that statement. It's definitely not a multiplication. Okay? Sometimes we also say y equals f at x. Okay? Now, there is absolutely nothing magical about the symbols x, y, or f. We could use A, B, and happy face instead. Okay? So nothing at all special. They're just kind of traditional, but you should use whatever variables make the most sense and will remind you of the unknown quantities that underlie them, or the varying quantities that underlie them, and the relationship between them. Now here are some examples of functions. You'll notice that I have given all sorts of different symbols for the names of the functions themselves and also for the independent variable. And here we see that there's an actual equation for each one. So that tells us how, if I take a particular input, x, my independent variable, I can get a certain output. I just have to calculate it. So what I have here are 5 different functions. Each one has its own rule to tell you how to take an input and turn it into an output, or find its corresponding output. Now, we can of course plug real numbers into our functions, but we can also plug in algebraic expressions. So let's take a look at how this all works and get used to this notation. We call this functional notation. So we're going to flip over the page now, but we'll be referring to these functions right here. Okay, so keep them in mind, keep an eye on them. We'll use them to calculate function values. So our function from the previous page, f, if we plug in x equals 2 and figure out what the output should be, well, what I'll do is I'll replace everywhere I see an x in the function with a 2 in brackets. I'll just write it off to the side here just to remind you what f was, but you can just look back on the last page, it's right there. So everywhere I see an x here, there, I'll replace it with a 2 in brackets. And then I end up with an expression that I can calculate. I just need to remember my order of operations. So we have 12 minus 10 plus 1, that's 3. Now g of negative 7, well, now we're talking about a different function. If you look at the last page, you'll see that g of t was 5t minus 19. Okay? So this is a totally different function. It has its own rule. So everywhere I see a t, there's only one place, I'll replace it with a negative 7. And I'll calculate that. Now, of course, I'm not limited to just plugging numbers into my functions. I can also put in other algebraic expressions. So if I plug c into g, what does that look like? Well, just like I would with a number, everywhere I see a t, I'll replace it with a c. That may not seem that exciting, but if you plug in something other than just a single symbol, say in the next example where we have 7z plus 1 being replaced as the independent variable in g, we would have 5 times 7z plus 1, don't forget your brackets, minus 19. And if I simplify that, I end up with a new expression that now talks about z. Now, Our functions can be exciting. Okay, we can end up with all sorts of complicated functions with all sorts of complicated rules. This symbol here, by the way, that's phi. In fact, it's capital Phi. It's a Greek letter. We'll use some Greek letters, especially during our trigonometry unit. That's the traditional way to call your variables. And when I get down to my last example here, remember that m of w, that function, was equal to 6 minus 3w. Okay, that was the function. So if I replace the w with 5, something happens that's a little bit interesting. I end up under my square root sign with -9, 6 minus 15. And of course, we know that there's no real number that is the square root of -9. There's no number you can square to get -9. No real number, at least. Okay? So what we would say is that m of 5 is undefined. So what's just happened here? We've tried to plug in a certain value for w that's not allowed in that function. So that's something we'll keep an eye on, and we'll talk about it soon. But this is a key idea. Some values cannot be plugged into certain functions. And that'll be something that we'll study carefully. Of course, it depends on the function itself, what properties that function has. Here, if you try to plug 5 into the previous functions, it'll pretty much, well, it'll work. But here, it won't for m. So there are certain values that can be plugged into m and certain ones that can't. We'll study those quite closely. Thank you.